There is a place in the universe where time stops, not slows down, not stretches, stops, where the laws of physics, every equation, every principle, every certainty that science has ever produced, break down completely and produce answers that make no sense, where space itself falls inward faster than light can escape, where matter is compressed to a point of infinite density that our mathematics cannot describe, that our instruments cannot measure, and that our minds, shaped by millions of years of evolution on a comfortable rocky planet, cannot truly picture. We call it a black hole. And here is the fact that stops most people cold when they first truly understand it. There are black holes in the universe so large that if you fell into one, if you crossed the boundary and began falling toward the center, you would not know it. No alarm would sound. No force would press against you. No sensation would tell you that you had just crossed the point of no return. You would simply be falling, peacefully, quietly, into something from which nothing, not matter, not light, not information of any kind, has ever returned. And the strangest part, the part that keeps physicists awake at night, is what happens next. Because depending on who you ask, depending on which framework of physics you apply, the answer is completely different. According to one framework, you fall forever, approaching but never reaching the center, time stretching infinitely around you. According to another, you are instantly destroyed at the boundary, burned to nothing by a wall of fire before you ever cross it. According to a third, you pass through safely and emerge somewhere else entirely. These are not fringe theories. These are not science fiction. These are the best answers that the greatest physicists alive have been able to produce, and they cannot all be right. Welcome to the most contested, most mysterious, most strange frontier in all of modern science. Welcome to the black hole information paradox. Before we fall in, we need to understand what we are falling into. A black hole is not a hole. It is not empty space. It is not a vacuum cleaner that sucks things in from across the galaxy. It is an object, an extraordinarily dense, extraordinarily massive object, the most extreme object that the laws of physics permit to exist. Here is how one forms. Massive stars, stars many times larger than our sun, burn for millions of years, fusing hydrogen into helium, helium into carbon, carbon into heavier and heavier elements, all the way up to iron. This fusion process produces the energy that makes a star shine. More importantly, it produces the outward pressure that holds the star up against its own gravity. Iron is the end of the line. You cannot fuse iron to release energy. Iron fusion absorbs energy rather than producing it. When a massive star builds an iron core, the fusion stops. The outward pressure disappears. And gravity wins. In a fraction of a second, less time than it takes you to blink, the core of a star that has been burning for millions of years collapses. The outer layers, suddenly unsupported, fall inward at a quarter of the speed of light, hit the collapsing core, and bounce outward in the most powerful explosion in the observable universe. A supernova. The explosion is so bright that for weeks it can outshine the entire galaxy it lives in. Every star in the galaxy, combined, and still this single dying star burns brighter. But the core, the iron heart of the star, continues to collapse. If the core is massive enough, nothing stops it. Not the pressure of electrons resisting compression, not the pressure of neutrons packed together. Nothing. It collapses to a point, a singularity, a region of space where density becomes mathematically infinite, where the curvature of space-time becomes mathematically infinite, where our equations produce the number that physicists most dread. They produce infinity, and infinity in physics is not an answer. It is a confession that our mathematics has broken down, that our theories have reached their limit, that we are describing something we do not yet truly understand. Around that singularity, at a specific distance determined by the mass of the object, is the event horizon. The point of no return. Cross it, and you are inside. Inside a region of space where the escape velocity, the speed required to escape the gravitational pull, exceeds the speed of light. And since nothing travels faster than light, nothing escapes. Not matter, not radiation, not information, not even time as we understand it. The event horizon is one of the strangest boundaries in the universe. It is not a surface. There is no wall, no barrier, no physical structure marking the edge. If you were falling toward a sufficiently large black hole, one with a mass billions of times that of our Sun, you would cross the event horizon without feeling anything at all. No jolt, no alarm, no change in the light around you. You would simply be inside. The reason for this is related to what Einstein told us about gravity. Gravity is not a force, in the Newtonian sense. It is a curvature of space-time. Mass curves the fabric of space and time around it, and objects follow the curves. They fall not because something is pulling them, but because the geometry of space itself is directing them inward. At the event horizon of a large black hole, the curvature of space-time is severe, but not, from your perspective as a falling observer, immediately overwhelming. You are in free fall. And free fall, Einstein showed, us feels like weightlessness, like floating. The same weightlessness astronauts feel in orbit, the same feeling that briefly overcomes you at the top of a roller coaster. You would feel that, peacefully, as you crossed the boundary from which nothing returns. But here is where it gets strange. From the perspective of someone watching you fall from a safe distance, someone hovering far above the event horizon, observing through an extraordinarily powerful telescope, something completely different would appear to happen. They would watch you fall. They would watch you approach the event horizon. And as you got closer, they would notice something odd. You would appear to slow down. Not because you are slowing down. From your perspective, you are falling normally. But because the extreme gravity near the event horizon is warping time itself. Time runs slower in stronger gravitational fields. This is the same time dilation we discussed in the context of Einstein's relativity. The same effect that makes GPS satellites tick at a different rate than clocks on the ground. Near the event horizon, this effect becomes extreme, catastrophically extreme. From the outside observer's perspective, you would appear to slow more and more as you approached the horizon. Your image would redden, the light from you stretching to longer and longer wavelengths as it struggled to escape the gravity. Your movements would become imperceptibly slow. And then, as you approached the horizon itself, you would appear to freeze, suspended, motionless, an image of you, reddening and fading, stretched across the surface of the event horizon for what would appear, from outside, to be eternity. You would never appear to cross. But from your perspective, you crossed long ago. Two observers, one event, two completely different, completely irreconcilable descriptions, both of them according to the laws of physics, Correct. This is not a paradox of perception. This is a paradox of reality. And it is the beginning of one of the deepest unsolved problems in all of science. Before we dive into the paradox at the heart of black hole physics, there is something visceral we need to address. What physically happens to your body as you fall into a black hole? The answer depends entirely on the size of the black hole. For a stellar mass black hole, one formed from the collapse of a single massive star, with a mass perhaps 10 to 50 times that of our Sun, the event horizon is small, perhaps a few tens of kilometers across, and the gradient of gravity near that event horizon is extreme. Not just strong, extreme in the sense that the gravitational pull on your feet, slightly closer to the singularity than your head, is vastly greater than the pull on your head. This difference in gravitational force across the length of your body is called a tidal force. On Earth, you experience tidal forces too. They're what create the ocean tides. But they are far too weak to feel in your body. Near a stellar mass black hole, they are not weak at all. Your feet would be pulled toward the singularity with dramatically more force than your head. The difference would be enough to stretch you, literally stretch you, pulling your body into a long, thin strand of matter, atoms separating, molecular bonds breaking, your body drawn out into a thread kilometers long before you reached the singularity. Physicists call this process spaghettification. Not a very dignified end, but for a supermassive black hole, one with a mass billions of times that of our Sun, like the monster that sits at the center of the galaxy Messier 87, whose image we captured in 2019, the event horizon is enormous, billions of kilometers across, and the tidal forces at the event horizon, spread across that vast distance, are relatively mild. Mild enough that a human body would survive crossing, that you would feel nothing unusual as you passed through. The spaghettification would come later, much later, as you fell deeper toward the singularity and the tidal forces finally overwhelmed you. But at the moment of crossing, nothing, just the quiet of free fall, and the knowledge, if you somehow knew where you were, that you had just entered a region of the universe from which you would never leave. What happens to time inside a black hole? This is where the strangeness becomes almost incomprehensible. We established that time runs slower in stronger gravitational fields. This is not a theory or an approximation. It is a measured, confirmed, experimentally verified fact. GPS satellites correct for it every day. Atomic clocks at different altitudes tick at measurably different rates. Near the event horizon of a black hole, this effect is enormous. Time, for a falling observer, runs dramatically slower relative to an observer far away. At the event horizon itself, from the outside perspective, time appears to stop entirely. But from the inside perspective, from the perspective of someone who has crossed, time continues. It runs forward. Events continue to happen. Thoughts continue to occur. The falling continues. There is, however, something deeply strange about the direction of time inside the event horizon. In normal space-time, you can move freely through space, left or right, forward or backward, up or down, but you can only move in one direction through time. Forward. Always forward. The future is the direction you cannot avoid moving toward. Inside a black hole, this changes. The mathematics of general relativity, Einstein's theory of gravity, tells us that inside the event horizon, the singularity is not a place. It is a time. The singularity is in your future. unavoidably, inescapably, in the same way that tomorrow is in your future. You cannot avoid it any more than you can avoid the passage of time. Every direction in space, inside the event horizon, leads to the singularity, not because space is curved in an ordinary way, but because what was the time dimension and what were the space dimensions have, in a sense, exchanged roles. The singularity is not somewhere you go. It is something that happens to you. It is a moment, a final moment, and between crossing the event horizon and reaching that final moment, depending on the mass of the black hole, you might have seconds or you might have hours, but no amount of rocket thrust, no amount of energy expenditure can delay it. The singularity is in your future, the way death is in everyone's future. And inside a black hole, it is considerably more certain and considerably more prompt. Now we reach the heart of the matter. The problem that has occupied some of the greatest physicists alive for nearly 50 years. The question that Stephen Hawking spent decades wrestling with, and that remains, even after his death, unresolved. The black hole information paradox. To understand why it is a paradox, you need to understand two things. The first is a principle from quantum mechanics called unitarity. Quantum mechanics, the physics of the very small, operates according to strict rules. One of the most fundamental is that information is never destroyed. You can scramble information, you can hide it, you can transform it beyond recognition. But the information is always there, in principle recoverable. If you burn a book, the information in the book still exists, encoded in the exact positions, velocities, and quantum states of every smoke molecule, every ash particle, every photon of light released by the fire. In principle, if you could track every particle perfectly, you could reconstruct the book from the smoke. This is not a practical claim. It is a fundamental principle of how quantum mechanics works. Information is conserved. Always. Without exception. The second thing you need to understand is Hawking radiation. In 1974, Stephen Hawking made the most important theoretical discovery of his career. Using a combination of quantum mechanics and general relativity, he showed that black holes are not perfectly black. They glow, very faintly, extraordinarily faintly. But they emit radiation, now called Hawking radiation, as a consequence of quantum effects near the event horizon. The mechanism involves quantum fluctuations. In the quantum vacuum, in what we think of as empty space, pairs of particles are constantly popping into existence and annihilating each other, too brief to be detected. Near the event horizon, sometimes one particle of a pair falls in while the other escapes. The escaping particle becomes real. Hawking, radiation. The black hole loses a tiny amount of mass in the process. Over an extraordinarily long time, far longer than the current age of the universe for any black hole of significant mass, this process causes the black hole to slowly lose mass and eventually evaporate completely. And here is the paradox. The Hawking radiation that carries away the black hole's mass is, according to Hawking's original calculation, completely random. It carries no information about what fell into the black hole. When the black hole evaporates completely, all the information about everything that ever fell in, every book, every star, every civilization, is simply gone, destroyed. But quantum mechanics says information cannot be destroyed. We have a contradiction. A direct, flat, irreconcilable contradiction between two of the most successful theories in the history of physics. general relativity and quantum mechanics cannot both be right about black holes. One of them is wrong, or both of them are incomplete. Or there is something we are missing entirely. This is the information paradox. And it is not a philosophical quibble. It is a crack running through the foundation of our understanding of reality. The information paradox has generated some of the most creative and radical thinking in theoretical physics. The proposed solutions are extraordinary, and they cannot all be right. The first major proposal is called the firewall. In 2012, 4 physicists, Ahmed Almhairi, Donald Marolf, Joseph Polchinski, and James Sully, published a paper arguing that the smooth, peaceful crossing of the event horizon that general relativity predicts is simply wrong. They argued that in order to preserve the information in Hawking radiation, to satisfy quantum mechanics, the event horizon must be surrounded by a wall of high-energy radiation. A firewall, an invisible but lethal boundary that would instantly destroy anything crossing it. In this picture, there is no peaceful free fall across the event horizon. The moment you touch the boundary, you are incinerated. The information of your existence is preserved in the radiation, and you never reach the interior. This solution saves quantum mechanics, but it destroys general relativity's prediction that crossing the event horizon is uneventful. Einstein's theory says you feel nothing at the boundary. The firewall says you are instantly burned alive. They cannot both be right. The second proposal comes from string theory and is called the fuzzball. In string theory, a framework that attempts to unify quantum mechanics and general relativity by replacing point particles with tiny vibrating strings, black holes are not empty interiors with singularities at their centers. They are fuzzballs, dense, tangled configurations of strings that fill the entire region inside the event horizon. No empty interior, no singularity. Just strings, all the way down. In this picture, the event horizon is not a boundary in empty space, it is the surface of the fuzzball itself. And the information of everything that fell in is encoded in the quantum states of the strings on the surface. The information is preserved. The singularity is avoided. But general relativity's picture of the black hole interior is completely wrong. The third proposal, and perhaps the most radical, comes from a connection between 2 seemingly unrelated areas of physics discovered in 1997 by physicist Juan Maldacena. He showed that a theory of gravity in a region of space is mathematically equivalent to a quantum theory without gravity on the boundary of that region. This equivalence, called the ADS/CFT correspondence, suggests something extraordinary about black holes. Everything that happens inside a black hole can be completely described by quantum physics on the boundary, on the event horizon itself. The interior is not a separate place. It is a holographic projection of the boundary. In this picture, called the holographic principle, the universe itself may be a hologram, a 2-dimensional surface of information that gives rise to the experience of 3-dimensional reality. And a black hole, in this framework, is not a place where information is lost. It is a place where information is maximally scrambled, hidden in the most complex, most entangled quantum state imaginable, but never destroyed. For most of the history of black hole physics, these objects existed only in mathematics. Solutions to Einstein's equations, theoretical constructs, things that the physics said must exist, but that no one had directly observed. That changed. On September 14, 2015, At 5:51 in the morning Eastern Time, two detectors separated by 3,000 kilometers, the LIGO gravitational wave observatories in Louisiana and Washington, simultaneously detected something. A ripple in space-time, a gravitational wave, a distortion in the fabric of space and time itself, produced by two black holes, each roughly 30 times the mass of our Sun, spiraling toward each other at a significant fraction of the speed of light and merging into a single, larger black hole. The event had occurred 1.3 billion years ago, in a galaxy 1.3 billion light-years away. The gravitational waves had been traveling at the speed of light for 1.3 billion years, and when they arrived at Earth, they compressed and stretched the LIGO detectors by a distance 20 times smaller than the diameter of a proton. 20 times smaller than a proton, and we detected it. The signal lasted less than a second, but in that second, more energy was released than all the stars in the observable universe combined emit in that same second, in gravitational waves, silent, invisible, passing through everything. We felt it. Einstein had predicted gravitational waves in 1916. It took us a century to build instruments sensitive enough to detect them. Then, on April 10th, 2019, something even more extraordinary happened. The Event Horizon Telescope, a network of radio telescopes spread across the entire Earth, linked together to function as a single dish the size of our planet, released an image. The first direct image of a black hole. Specifically, of the supermassive black hole at the center of the galaxy Messier 87, a monster 6.5 billion times the mass of our Sun, 55 million light-years away. The image showed a bright ring of glowing gas, the accretion disk, matter heated to millions of degrees as it spirals inward, surrounding a dark central region. The shadow of the event horizon, backlit by the brilliance of the infalling matter. It was blurry, it was orange and indistinct. By the standards of modern photography, it was unremarkable, and it was one of the most important images in the history of science. A black hole, real, imaged, confirmed. In April 2022, the same team released a second image, this time of Sagittarius, a star, the supermassive black hole at the center of our own Milky Way galaxy. 4 million solar masses, 26,000 light-years from Earth. The black hole at the center of our own galaxy. Photographed. We are no longer speculating about whether black holes exist. We have seen them. We have heard them. We have felt the ripples they make in the fabric of space-time. They are real, and the questions they raise, the information paradox, the nature of the singularity, what happens inside, are real questions about the real universe that we genuinely do not yet know how to answer. Stellar mass black holes, the ones formed from collapsing stars, are extraordinary. But they are, in a sense, the ordinary variety. At the center of almost every large galaxy in the observable universe sits something far more extreme. A supermassive black hole, not 10 or 50 times the mass of our Sun. Millions, billions, sometimes tens of billions of times the mass of our Sun. Objects so massive that their event horizons are measured not in kilometers, but in light hours, light days, light years. The black hole at the center of Messier 87, the one we imaged in 2019, has an event horizon so large that our entire solar system would fit comfortably inside it. Our entire solar system, inside the event horizon, with room to spare. and M87 is not the largest known. The black hole at the center of the quasar TON 618, a luminous active galactic nucleus, has a mass of approximately 66 billion solar masses. Its event horizon is approximately 40 times larger than the orbit of Neptune. How these monsters formed is itself an unsolved mystery. They appear to have existed when the universe was very young, within the first billion years. Growing a black hole to billions of solar masses in a billion years strains our models of how they accumulate mass. Did they grow from stellar mass black holes, consuming matter at extraordinary rates? Did they form directly from the collapse of enormous clouds of gas in the early universe? Or did they form through some process we haven't yet imagined? We don't know. What we do know is that they play a central role in the evolution of galaxies. The supermassive black hole at the center of a galaxy and the galaxy itself appear to grow together, their masses correlated in ways that suggest they shape each other's development. The monster at the center and the city of stars surrounding it, locked together across billions of years of cosmic history. And at the center of our own city of stars, 26,000 light years from where you are sitting right now. Sagittarius, a star waits, quiet at the moment by the standards of active galactic nuclei, not currently consuming large amounts of matter, not producing the blazing jets of energy that make quasars visible across the universe. Just sitting there. 4 million solar masses, the gravitational anchor of our galaxy, the dark heart of the Milky Way. We have been circling it throughout this entire video. The singularity, the point at the center of a black hole where the mathematics of general relativity breaks down completely, where density becomes infinite, where space-time curvature becomes infinite, where our best theory of gravity produces answers that are, literally, meaningless. Infinity is not a physical measurement. Nothing in the real universe is actually infinite. When our equations produce infinity as an answer, it means one thing and one thing only. Our equations are wrong, or rather, incomplete. General relativity is extraordinarily accurate everywhere we have tested it. It predicted gravitational waves a century before we detected them. It predicted the bending of light around massive objects. It predicted the precise rate at which clocks run slower in gravitational fields. It has passed every experimental test we have subjected it to. But it breaks down at the singularity. Because at the singularity, quantum effects become important. The scales involved, the densities, the curvatures, are so extreme that the quantum nature of matter and energy cannot be ignored. And general relativity does not include quantum mechanics. To describe what actually happens at the singularity, to replace the nonsensical answer of infinity with a real physical answer, we need a theory that combines general relativity and quantum mechanics, a theory of quantum gravity. We do not have one. String theory is a candidate. Loop quantum gravity is a candidate. There are others, but none of them has been confirmed by experiment. None of them has made a prediction that we have been able to test and verify. The singularity sits at the center of black hole physics like a locked door. We know it is there. We know that behind it lies something, some physical reality, some quantum description of what actually happens when matter is compressed to the ultimate extreme. But we do not have the key. The singularity is not just the center of a black hole. It is the frontier of human knowledge, the place where our understanding of the universe runs out, where the equations stop working and the honest answer is, we don't know. And in science, in real science, as opposed to the comfortable certainties of textbooks, those 3 words are not a defeat. They are an invitation. Step back from the mathematics for a moment. Step back from the information paradox and the firewalls and the fuzzballs and the holographic principle, and consider what the existence of black holes tells us about the kind of universe we live in. We live in a universe that contains regions of space from which nothing can escape, where the geometry of space-time curves so severely that it closes in on itself, where matter can be compressed to densities our language has no words for. We live in a universe where time is not a constant backdrop, but a physical quantity, something that can be stretched and warped and, at the event horizon, effectively stopped. We live in a universe where 2 of our greatest theories, the theory that describes the largest scales of reality and the theory that describes the smallest, are fundamentally incompatible with each other, where the universe we observe demands a reconciliation that we have not yet achieved, and we live in a universe where, at the center of our own galaxy, 4 million times the mass of our sun sits in darkness, shaping the orbits of the stars around it, the gravitational anchor of everything we have ever seen in the night sky. That is not an abstract fact. That is the reality of the place we live in. The black hole at the center of the Milky Way is not a distant curiosity. It is a neighbor, a presence, something that has been there since before Earth formed, before the sun ignited, before the solar system coalesced from a cloud of gas and dust 4.6 billion years ago. It was there at the beginning of our world. It will be there long after our world is gone, long after our sun has burned through its hydrogen and swelled into a red giant and consumed the inner planets and collapsed into a white dwarf and cooled over trillions of years to a dark cinder. Long after that, Sagittarius A star will still be there, slowly consuming matter, slowly growing, slowly over time scales that make the current age of the universe look like an eye blink, evaporating through Hawking radiation. If Hawking was right about Hawking radiation, which the information paradox suggests may require revision, the universe is stranger than we thought. And black holes are perhaps the clearest demonstration of exactly how strange it is. Look at that image. An orange ring of glowing gas, a dark center, blurry, indistinct, nothing like the sharp drama of a Hollywood rendering. And yet, that dark center is a region of space 6.5 billion times the mass of our sun, 55 million light-years away, whose boundary marks the edge of the observable, the point beyond which nothing has ever sent back a signal. We made that image with a telescope the size of the Earth. We made it by linking radio dishes on 6 continents, synchronizing them to atomic clocks, collecting petabytes of data, and spending years writing algorithms to combine it all into a single coherent picture. We made it because, a century ago, a man sitting alone in a room in Berlin wrote down a set of equations that described how mass curves space-time, equations that predicted, as a mathematical consequence, that regions of space must exist from which nothing could escape. He called them a mathematical curiosity. He doubted they could be real. He was wrong about the doubt. We know that black holes are real. We have seen them. We have heard the gravitational waves of their collisions. We have measured the orbits of stars dancing around the dark mass at the center of our galaxy. And we know, with equal certainty, that we do not understand them. Not fully. not deeply, not at the level that would let us say with confidence what happens inside, what becomes of the information that falls in, what replaces the singularity when a proper theory of quantum gravity finally tells us the truth. The black hole is not a solved problem with a known answer. It is an open door, a door standing at the boundary between what we know and what we don't, between the physics we have built and the physics we have not yet imagined, between the universe as we understand it and the universe as it actually is. And somewhere on the other side of that door, somewhere in the mathematics we haven't yet written, the experiments we haven't yet designed, the ideas we haven't yet had, is the answer to the deepest question black holes ask. What is space? What is time? What is information? What is reality at the level where our two greatest theories crack and fail and demand something new? We don't know yet, but we are asking. And asking in the end is how every answer in the history of science began.